Can we trust time travel theories? What if I told you that you are, right now, a time traveler? It's true, and even crazier, we have the receipts to prove it. Albert Einstein's theories of relativity laid out the roadmap for jumping into the future. But what happens when we try to throw the car in reverse? Can we really rewrite the past, or would we just get tangled in a web of paradoxes that could unravel reality itself? Let's figure out if time travel is something we can actually trust. Chapter 1. The One-Way Ticket Forward. When you hear time travel, you probably picture a flashy machine and a convoluted plan to mess with history. But the most legit form of time travel is way more subtle, and it only goes one way, forward. The guy who handed us the keys to this whole mind-bending idea, none other than Albert Einstein. Over a century ago, his theories of special and general relativity took our old rigid concept of time and shattered it into a million pieces. He showed us that space and time aren't separate things. They're woven together into a single, four-dimensional fabric called space-time. And this fabric isn't flat. It can be bent, stretched, and warped by mass and energy. Think of space-time as a giant trampoline. If you put a heavy bowling ball, like a planet or a star, in the middle, the fabric dips and curves. That curve is what we feel as gravity. But here's the kicker: this warping doesn't just affect space. It messes with time. This is called time dilation. General relativity tells us that the stronger the gravity, the slower time ticks. This isn't just a wild theory, it's a proven fact we use every day. GPS satellites orbiting Earth are in a weaker gravitational field than we are, which means their clocks actually run faster. The two effects of relativity, clocks running slower because of their high speed, special relativity, and faster because of weaker gravity, general relativity, combine for a net effect. The clocks on GPS satellites get ahead of ground clocks by about 38 microseconds every single day. Without constant corrections for this, your GPS would send you off course by about 10 kilometers or 6 miles daily. Special relativity throws another twist into the mix. It says the faster you move through space, the slower you move through time compared to someone standing still. Scientists proved this in a brilliant experiment where they put hyper-accurate atomic clocks on jets and flew them around the world. When the planes landed, the clocks that had been flying at high speed were fractionally behind the clock that stayed on the ground. This means astronauts on the International Space Station are literally time travelers, constantly jumping into the future, even if it's just by tiny fractions of a second. They age just a little bit slower than we do. If we built a ship that could hit, say, 99.9% of the speed of light, this effect would be staggering. A few years for the astronauts could mean centuries have passed on Earth. They'd return to our distant future. So, traveling forward in time, it's not just possible, it's a fundamental feature of our universe. Chapter 2. The Turn, the Problem with the Past. Alright, so hopping into the future is on the books, but what about a round trip? What about going back to the past? This is where things get really weird. While Einstein's physics gives us a one-way ticket forward, going backward is a completely different animal. Here, we leave the world of proven science and enter the land of theoretical speculation and logical nightmares. General relativity doesn't flat out forbid it. In fact, some exotic solutions to Einstein's equations hint at theoretical pathways that could loop back on themselves. They're called closed time-like curves, or CTCs. Think of space-time being so twisted, maybe near a spinning black hole or through a hypothetical tunnel called a wormhole, that a path forward could literally lead you back to where you started. But prying that door open invites a storm of problems that don't just test our technology, but the very foundation of cause and effect. Chapter 3. The Core Conflict, the Paradoxes that Break Your Brain. And this is where we run headfirst into the paradoxes, the logical knots that make backward time travel so tricky. These aren't just fun movie plots, they are serious roadblocks for any time travel theory. The most famous is the grandfather paradox. You know the one. You build a time machine, go back, and stop your grandparents from ever meeting. If you succeed, your parents are never born, which means you are never born. But if you were never born, who went back in time to begin with? The whole thing implodes. Your action erases the reason you could take the action in the first place. It's a massive contradiction that stories from Back to the Future to The Terminator have wrestled with. Then there's the more subtle, more sinister bootstrap paradox, also known as a causal loop. This isn't about changing the past, but about things that exist without ever being created. Picture this. A massive Shakespeare fan worries all his plays might be lost to history. So, he takes a complete works anthology back to the 16th century, finds a young, struggling playwright named Will Shakespeare, and gives him the book. Shakespeare, in turn, just copies the plays and publishes them. So, where did Hamlet come from? Shakespeare copied it from the book, but the book was made from Shakespeare's plays. The information is trapped in a closed loop, with no origin. It just is. This kind of paradox, where an object or idea has no starting point, throws our whole understanding of causality out the window. It suggests a universe where effects can just exist, without a cause. The mind-bending German series Dark masterfully explores these inescapable loops. These paradoxes seem to suggest that the universe has a pretty strong security system to protect its own logic, making any trip to the past either impossible or incredibly dangerous. If your brain is melting from these paradoxes as much as ours is, and you love untangling the biggest mysteries of science, make sure you hit that subscribe button and ring the notification bell. We tackle questions like this every week, and you won't want to miss what's coming next. Chapter 4. The Search for a Way Out. You'd think these reality-breaking paradoxes would be a deal-breaker for physicists, right? Wrong. Instead, they've cooked up some truly brilliant, if highly theoretical, ways around them. And the solutions are just as wild as the problems. One of the most elegant is the Novikov self-consistency principle, cooked up by Russian physicist Igor Novikov. This principle basically says that you can travel to the past, but you are absolutely, positively forbidden from changing it. The probability of any event that would create a paradox is zero. The laws of physics themselves will conspire against you. So, back to the grandfather paradox. According to this principle, if you tried to stop your grandparents from meeting, you'd fail. Maybe you'd slip on a banana peel. Maybe your time machine would conk out. Whatever happened, your actions, knowingly or not, are already part of history. You wouldn't be changing the past. You'd be fulfilling it. In this view, there's only one timeline. It's set in stone, and you're already a part of it. But there's another, even wilder solution: the many-worlds interpretation of quantum mechanics. This theory suggests that every time a quantum event has more than one possible outcome, the universe splits, creating a separate, parallel universe for each one. In the context of time travel, this means if you go back and change something, you don't alter your own past. Instead, your action just creates a brand new timeline. So you could go back and prevent your grandparents from meeting. In that new universe, you'll never be born. But it has zero effect on the universe you came from, where you were still born and still built that time machine. You haven't rewritten history. You've just hopped onto a different branch of reality. This sidesteps the paradox by creating an infinite number of timelines where every possibility can happen without contradiction. On a much smaller scale, scientists have even started running quantum time travel simulations, using quantum entanglement where two particles are linked so that an action on one instantly affects the other. Researchers have found ways to simulate retroactively altering a particle's past state. These aren't time machines for people, but they show that at the quantum level, the rules of cause and effect might be a lot weirder than we think. Conclusion: a question of trust. So, where does that leave us? Can we trust time travel theories? Well, like time itself, the answer is relative. For traveling to the future, it's a definite yes. Time dilation is built on Einstein's proven theories. We see its effects constantly, and, with enough power, a leap into the future is a real physical possibility. But for going to the past, our trust has to be a bit more theoretical. The doorways that might let us go back, closed time-like curves, and wormholes are mathematically plausible, but they're still just speculation. And even if we found one, we'd come face to face with paradoxes that shake the very logic of reality. While creative solutions like the self-consistency principle or many worlds show it might not be logically impossible, they remain completely untestable ideas. They fix the paradoxes, but only by adding new cosmic rules we've never seen. So, can we trust the theories? The science says, maybe. The physics leaves the door cracked open, but the paradoxes force us to rethink everything we know about cause and effect, free will, and reality itself. We may not be visiting the dinosaurs anytime soon, but the quest to understand time travel pushes us to confront the deepest mysteries of our universe. What do you think? If you had a time machine that only went to the past, would you risk it? Let us know in the comments below.